and you expand this node. Let's say you get 3 children in this particular case. Okay? And let's say this is, so this is 0.1, this is 0.3, this is 7. So you take minimum of these. That is the node, the cost, the G value for any node that is just about more than the previous bound. And say that's the new bound. You see what I just said? It's kind of, you have to keep track of this. So the bounds are set during the search. You see what I'm saying? I basically first I'm only looking at this one node, and then when I expand this, I get these new nodes, right? And then I see which is the node whose G value is just crossing the previous G bound. That guy becomes the new bound. Why should we shiver when we think about this? Because every time you expand the depth, expand the limit, one node will come in. So the number of iterations for iterative deepening depth first search was how many? If the goal node is at depth D, how many iterations did you have to do in the worst case? D iterations. If the goal node is still at depth D, but the edges have non-uniform costs, in the worst case, how many iterations does iterative deepening uniform cost search have to do? B power D. That's bosoness. It was bad enough when you thought IDDFS and thought, how can it make sense? You're doing repeated work. How can it be a good idea? And then we sort of hand waved, we showed some geometric series summation business in the textbook and pointed out that guys, iterative deepening depth first search will not be worse than the average cost of normal breadth first or normal depth first. It's at most will be worse by B plus 1 by B minus 1 factor. B plus 1 by B minus 1 factor, where B is the branching factor. Which is why iterative deepening depth first search is great. Even in the worst case, that's pretty good. On the other hand, when you have G value cutoffs for the search tree, then you may well do, in the worst case, B power D number of B power D number of iterations. And there it would no longer be B plus 1 by B minus 1. And that would be a bad idea. So when people do iterative deepening versions of uniform cost search at the non-uniform edge cost cases, they are hoping that the problem is such that the edge costs are hopefully sort of integral and they are not taking too many different values. If they are not taking too many different values, what will happen is, as soon as you open the door a little bit wider, more than one person comes in, more than one node comes in, which is good for you. If only one node comes in every time you open a gate, you are screwed. You will be doing B power D times opening of the gate. Whatever I just said actually holds for IDA star too. In the case of IDA star, instead of deciding what is the next G value cutoff, you will decide what is the next F value cutoff, where F is written as G plus H, which we will talk about H in a minute. Okay? That's the deal. So there are properties. Okay, so I'm not sure, any questions about anything that I have been said? Okay, good. So I will just quickly go through this. These are. I just want to show that these examples exist in the slides, and you should definitely work through them. So this is a directed graph, and if you try to search this directed graph, normally the question is the order in which nodes get expanded. Okay, so, and assume that this goal node is G. I mean, this G is a goal node, so when you pick G up for expansion, you stop, essentially, that's the idea. Okay, so in fact, what I will do is I will go here. This is a rather busy slide, but actually it's me hand, basically walking you through each of the algorithms on that little graph using node notation, where a node is a data structure which has one field which corresponds to the graph node, graph vertex. Search node is different from graph vertex, because sometimes you can come to the same search node in multiple paths, and each time it's a different search node. Okay, so for example, what we are doing in this particular case is I started with node N1, which is A, and if I'm doing breadth first search, then I will put it on the queue, and then I will go to the queue and say, give me who is the first one I put in, and it will give N1 back. Then I'll expand, and then I'll first ask, is N1 a goal node? Before expanding a node, I have to ask, is it a goal node? If it is a goal node, you stop and declare victory and say, I'm done. And in fact, if the node is a goal node, typically in many cases, you want the path you have taken from the root node to come to this search node. That's not too hard, because the data structure will always put a pointer to the search node which got expanded to give this node. And so if you follow the pointers back all the way to the root node, then you got the reverse of the path. Right? Okay? So the only difference is in the case of breadth first, these two guys will come in, N2 and N3. Those of them will both be put on the queue, N2 and N3. And then you will go back to the queue, and whenever you take a node for expansion, you remove it from the queue. Okay? And then you go to N2, and you go to the queue, N2 happens to be there. Notice that the order in which N2 and N3 are put doesn't matter. We just assume, for all of us to get the same answer, we'll assume left to right precedence. But that's not important here. Okay? So N2 will be picked up. N2, when it gets picked up, N2 corresponds to the node B in the graph. When you expand node B, child generator function says, I will give you the graph node C. So now you make a brand new search node, whose graph node happens to be C, which has a child, the parent pointer to the previous node. Okay? Now, as soon as this node comes, you don't check is it a goal or not. You just throw it onto the queue. Throw it onto the open list. In the case of breadth first search, the open list is a queue. Open list is a queue. Okay? So what that means is this N4C goes behind N3G on the queue. So next time you go back to the queue, you will pick N3G, because that's actually before N4. That's the magic. That's the reason why breadth first is guaranteed to look at any shallow node, expand any shallow node before it expands any deeper node. Because of which, the first time it finds a search node, which is a goal node, before expanding it checks is it a goal, and it's a goal, it's guaranteed to be optimal. You see what I'm saying? So the same thing is done in this picture for DFS and IDFS. And notice what happens for DFS. Essentially, when N4 comes in, N4 goes and sits on top of N3, because it's a stack. So in fact, one thing obviously, again, just as we know D is nothing but a special case of G, then you can actually talk about a prioritized queue. And the queue priority is what? In the case of breadth first search, the queue priority is a D of N. In the case of depth first search is almost minus D of n. Do you see what I'm saying? In the case of uniform cost search, the Q priority is G of n. And you would know by the time you get to a node how you got to the node. You don't get to say, I don't know how I got it. Which can happen if you are drunk, but search algorithms rarely ever get drunk. They don't know how to look forward in time, but they certainly know how they got there. At least the systematic search algorithms. They know exactly how they got there. That's their G value. G is always known with complete certainty in systematic search. Okay? So look at this if you want to make sure that you understood how breadth first, depth first, and iterative deepening depth first. Okay? Now when you have undirected graphs, what happens? What happens in the case of undirected graphs, essentially, is when you're expanding B, you again get A as well as C. So there was an A originally, some search node N0 corresponding to the state A, and then again there is one more A now, except you took circular path to come to this, a loopy path to come to A. Do you understand what I'm saying? Okay? So now what happens in that particular case, in these undirected graphs essentially, is you're going back to the same node more than once. And the worry of course is, can you not get into loops? And if you get into loops, you now come out. The most interesting part is that breadth first or uniform cost search, which is again breadth first, which is basically prioritized queue in terms of G value, they will always overcome any looping. They will always overcome any looping. Why? Because when you first came to A, its G value is 0. The second time you came to A, you went from A to B back to A. The only way the G value could be less than 0 is walking gives you high. Do you understand what I'm saying? If the edge costs are negative, are 0, then you can have loopy stuff, and basically that node keeps coming again and again and again. If you just ensure that the edge costs are positive, this is what they say, non-zero positive. Which is true in most words. Cost typically is not negative, unless you are one of those masochists. Okay? So in which case, if you are doing this for masochists, you have to change the problem. Okay? So if you are looking at the cost being basically, as long as each edge is positive value, even if it is only 1 times 10 power minus 70, which is still a positive number, if you remember from your old, these exponential notations. You're guaranteed to find optimal solution the first time you find a solution, if you're doing breadth first or uniform cost search. You see what I'm saying? As far as the depth first is concerned, all bets are completely off, because it can go into the loops. Okay? One interesting question in this scenario is when you're doing graphs instead of trees, essentially you're coming back to the same node more than once. You may come back to it infinitely more often. And while breadth first and uniform cost search are guaranteed to overcome this and find the node, the first time they say we found a goal node before expanding it and say this is a goal node, they're still guaranteed to be optimal. And the number of iterations they have to do essentially is bounded by the smallest edge cost. Because every time you go back on the road, at least that 1 times 10 power minus 17, let's say that's the smallest edge cost, at least that much increase you are doing to the cost, G value. So eventually, it would basically expand enough of that nonsensical stuff, and then you will come to the primary. Now, when you're thinking about it, you'll say, well, I understand, but I can change the algorithm. So there are two options. One is, I already wrote the algorithm, I don't want to change it. I wrote my Python code for uniform class search for trees. Now you're saying you have graphs, undirected graphs, and I'm not going to change it. And I've said that it's guaranteed to terminate one of these days. And the semester is long, and I have time, nothing but time. So let me just run it. Right? And you're guaranteed to terminate. Right? The question is whether or not before the semester is over, still is open. So then the question is, will you ever have a scenario where there is an optimal path to the goal which contains loops? Will there ever be such a case? Do you understand what I'm saying? Will you ever have a problem that has, so to go from A to the best goal, so I'll go from A to B, B to C, C to B, B to C, C to B, then D, then G. Will that ever be optimal? No, because if that is optimal, if you say that is optimal, I'll just stop the looping and you will still be optimal. And in fact, that you will still be reaching the goal. And that will have a lower cost. So that means the original one is not optimal. So the interesting thing that I said just now is, you don't know what the optimal path to the goal is. But you know that optimal path to the goal is guaranteed not to have any loops. So if you find loops, you can kill that path. And you're still guaranteed to reach optimal path. That's what dealing with graph search is. Basically, you want to stop whenever you found a search node which has been seen before, that means the search node corresponds to the world state which has been seen before. In this case, of course, it's our graph, so actually the graph node A, B, C, those are the world states. The search nodes are N1, N2, etc. So if the search node N7 happens to have the world node A, and you have seen A before, then you don't put this guy onto the queue. If you don't put the guy onto the queue, then there is nothing that's going to happen below that node. That entire subtree below that node has been killed. Very darn good. Okay? But this only works because we are saying that the edge costs are non-zero and positive. If the edge cost can be negative, then looping gives you happiness. So the more loops you do, the more optimal you are becoming. The shorter the cost is becoming because of the negative cost. And then all of this thing falls apart. Okay? So one interesting question, of course, is if you're doing this, if you want to stop the loops, then you just have to remember which node, right? Whether you saw this world state. So this is where we have to think in terms of some closed list. Closed list contains the list of world states that have been expanded ones. They've been closed. Right? And so the simplest idea that you will come up with is, whenever you get a new search node, you check if the word state corresponding it stays, it is on the closed list. There are two issues. One, checking whether the node is the same as another node. In our case, in the graph search, is this A and that is A equal to A, equality test. Imagine you are searching the space of some arbitrary graphs. That means each search node, each world state is an arbitrary graph. To check whether this graph is the same as this graph, you have to do graph isomorphism check. That's basically, graph isomorphism is one of those problems which is between P and NP. You still don't know. Pretty hard problem. So sometimes checking whether a state is a duplicate state, depending on the problem, can take highly significant computational resources. If the state just happens to be some single name or something, you can do equality test. If it is an actual structure, then you have to see equality of structures. This is more true often than you be led to believe if you only think in terms of graphs. The second, of course, is how many nodes are going to be sitting on the closed list. Remember, we were keeping this closed open list real small by doing depth first search, for example. It's only b times d plus b times d is the open list. But if I started throwing stuff onto the closed list, how big can the closed list become? Imagine you're buying these cans and you want to reduce the space consumed in the office. I'm only going to get 6 cans every time. So there's only 6 cans unopened. But then after I'm done with the can, I'll throw it into my room. That's the closed cans. Basically, I've been consumed cans. After some point of time, I have no room. I only have cans. You see what I'm saying? Junk is full of, the room is full of junk cans. That's the same thing that happens here. After a long time, closed list will contain most of the graph. That actually can be b power d nodes. B power d different nodes. And so you very carefully, I'm saying, I'm being extremely careful. I'm only buying 6 cans at a time. See how space efficient I am while the closed cans are pushing me out. Because they are like, you see what I'm saying? So as much as people think, let's put everything on the closed list, no, don't do it. Because if you put everything on the closed list, the list itself can become b power d, which is what you are trying to avoid to begin with. You see what I'm saying? So instead, you will then basically have to come up with the kind of nonsense that we come up with, which is I'll say, every week I'll only get like 6 cans, and every 3 weeks I'll throw away my garbage. So that the room is not full of closed cans. So reduce the number of nodes on the closed list. If you reduce the number of nodes on the closed list, you are not guaranteed that you won't ever expand a duplicate node. But if you are careful, you can expand, and you can at least start expanding some of the duplicate nodes. In particular, one thing that is true in many of the undirected graphs kind of scenarios is nodes wind up giving their ancestors back. You see what I'm saying? They just give their ancestors back. They don't give some cousins on the graph. They tend to give their ancestors back. So a cute idea is to essentially say, I will put on the closed list my ancestors to this node. So if any node, and in fact then I don't even need the closed list, because every node has pointers going all the way back to the root node. So whenever you get a new node, then check if the path to the ancestors contains this node again. If so, refuse to open. Just throw it away. That's an extremely good idea. In fact, that's what most of you should be doing, because that reduces significant amount of duplicate detection, duplicate one. It will still allow some cousins and distant cousins, being repeated. Yes? Okay. You are the first slide, very first try. So yes, I do, but that's a very silly question. Because I've been talking about it before. Yes, I do. So summary of uninformed search is that basically we look at summary of uninformed search, and then we also should remember problem state for the search node. We should also remember all this stuff that I talked about, handling loops. Okay, and then I want to say a little about the uniform class search and move to A-star search, make you think about it, and then we will. Okay, so in the case of uniform class search, essentially basically the tree here is, it turns out these are all integral values. The edge costs are integral values, so they're kind of nice. If they're real values, it's much worse. Right? Integral values kind of put some sort of a structure to the number of iterations that you have. Okay, so that's what was uniform class search, except the Q then was in terms of G values, not the D values. And it's a prioritized queue where the lower the G value, the first you would expand the node. Right? That's uniform cluster. Okay. So it turns out that it is complete. It also turns out it's optimal. The reason it is optimal is because essentially what I said, which is every node, every edge has positive cost. Every edge has positive cost. So here is actually a proof that you can provide. See the proof is. Right? So we'll talk about the proof in a minute, but in general, if you are, in a sense, instead of going level by level, you are going distance by distance by distance from the root node. So the circle, the concentric circles are the miles, not the depth. And so you are guaranteed that if you found a search node, a goal node in the 15th concentric circle, then, and you haven't found it up until then that must be the best distance goal node from the root node. That's uniform cost search. It looks as if uniform cost search is using a lot more information because it is using this edge cost. But as I told you, that's not the difference between informed versus uninformed search. You see what I'm saying? This is still blind search. It's just blind search with non-uniform cost edges. Okay, now the problem with that is, look at this kind of a tree. So again, in the normal uniform cost search, if I don't see anything else, then you are essentially doing breadth first search. But where the breadth is stuff, instead of going in terms of level by level by level, as I said, you're going G by G, the distance by distance by distance. Okay, which is basically the G value. So the problem with that is, while that is guaranteed to be optimal, that means when you find the solution, you will be guaranteed that you have found the first solution you found is the optimal solution. Okay, actually let me ask a very important question. Why do I need to guarantee optimality by proving beforehand? Why don't I allow algorithms to come and say, hey, here's the solution, I kind of think it's optimal. Why is that not a good idea? Exactly. Do people understand this? In fact, it's extremely important to understand that optimality is a global property. The only way I can tell whether the solution you gave is optimal or not is I spend my lifetime trying to come up with optimal solution and check if it actually is shorter than yours. Then why do I have you around? I could just do it myself. So search algorithms will say, hey, I kind of think it is optimal, they're useless. Either B or not B. There is no kind of B for optimality. Do you understand? It's extremely important. Which is why we focus on this optimality during the proof time. You give a certificate that even any bozo or any impatient or a patient bozo can use this search algorithm. When it says I have a solution, it's guaranteed to be optimal. And you don't do check on this by kind of a couple of times, let's do a empirical check and say, ah, this time you're right, this time you're right. That's not the way proof works. It's actually true forever. Any problem, if it says here's a solution, it will be optimal. Okay, that's true for breadth first, that's true for uniform cost. But in trying to give this guarantee of optimality, these search algorithms can essentially do too much work. There's a question of solution quality, which is whether you got the optimal solution or not. And there's a question of how much work did you do, which is how much computation did you do. We said that the memory cost of a search algorithm is approximately in terms of the open list and the closed list, right? What is the computational cost of a search algorithm? What is the biggest item that changes the computational cost of a search algorithm? I understand why, where is the time coming from? It's like saying space is space. Right? Space is not space. Space is the number of thingies on the open list. Okay? clearly computational cost is time, but how do you count the time in search algorithm? That doesn't mean anything. Expanded. Number of nodes expanded. That's the thing that you say, that you use as the yardstick. You see what I'm saying? Number of nodes expanded is the abstract comparison between two search algorithms. And say if it expands more nodes while giving the optimal solution than this other guy, then this one is more efficient. Okay, fine. So now think of guys like this. What? Yes.
Should it be
Uh-huh.
should we consider the value as well while considering the time complexity?
No, the main thing, again, this is, in computer science we do order of magnitude notation. The biggest time consumption happens for the expansion, node expansion. Space also, for example, there are other things that might take a little bit of space in the program. But the biggest space consumption for a search algorithm is the open list and the closed list.
If we are calculating the g-value to identify
Those are, yeah, I understand, that's like adding arithmetic numbers is different from, it's like saying the cost of expansion, let's say, is 15 units, and adding two numbers is 10 power minus 6 units. That's what I'm talking about. So this graph was quite nice. It's like, on this side 1, 1, 1, 2, G, and then this is 9. The point of this graph is, if you are not doing breadth first, you would have picked G first. If you are a depth first guy, left and right are basically interchangeable. It is likely to have, in fact, you would have picked G, right, if you're doing depth first search. Because it would have got B and G onto the open list. It would expand B, then it will expand G, and it will stop. And then it would say, well, I found optimal solution 9 units cost. And here you say, I can see the graph, and you are wrong. But if you have to look over the shoulders of your program, it's a useless program. Right? If you have to actually look over the claims of optimality, then there is no claim. Okay? So here actually this is a good scenario where it sort of shows why the distance by distance traversal of the search graph ensures that the first node you expand will actually be optimal. Right? Here is another example. Here, what I call bait and switch graph. This is the kind of nonsense that happens when they say, we are giving away free something in the Walmart, and you run to get it. And then they say, oh, that's over, but there is this other extremely costly stuff. And you say, I already spent time, I have to buy it. Okay, so here, these are all 0.1s. This is 25 units. This is 9 units. So the uniform class search gets B onto the queue and G onto the queue, and it says, G, you guys are useless, you're still 9 units costly, these are 0.1 units costly. And I get C,